So in the last video, I showed a diffusion in a pipe where we had fixed concentrations on the left side and on the right side. These were set to 10 milligrams per cubic meter and 0 milligrams per cubic meter. This was what we called Dirichlet boundary conditions, which also called the first type of boundary condition. And that means that the state variable is fixed at the boundaries. How did we enforce that? Well, down in the rates function, we set the dc dt, the derivatives, at all the ODEs, so that is at all the nodes, including the boundary positions, we set it to 0 to start with. And then down in the loop here, we only loop over the interior points, starting from 1 and ending at n exclusive. That means that dc dt will always be 0 for the left and the right boundaries. And if they are 0, then that means that the initial value that they had will never change. So we have no change over time, and therefore actually the initial conditions at the boundaries are just kept throughout the whole problem. Now we will change the problem a bit, and we will close the pipe on the left and right end. I have marked this with these vertical bars here. So the gas cannot escape from the pipe anymore. This also means that the concentration on the left side will decline over time because it diffuses to the right side, and in the end we should actually have an equal distribution of concentration in the whole pipe. Okay, so now obviously we have to do something different than last time, and we have to explicitly handle the derivatives at the boundary conditions. So by closing these ends of the pipe, it actually means that we have a flux that is equal to 0 at the boundaries. There's no flux across this barrier here. This situation where you fix the flux at the boundaries is called the Neumann boundary condition. And in this specific case, the flux is then equal to 0, which is the most used case of the Neumann boundary condition. Okay, so we know that the flux from Fick's law is J, which is equals to negative of the diffusion coefficient times the gradient. And we have now set up the problem such that this is equal to 0 at the boundary. So we can say it's 0. We can then take this part and discretize it using finite central differences. So we have that it is equal to I plus 1 minus 1 divided by 2 times dx here. And this is equal to 0. Then at the left boundary, we can put in the actual index. So that would actually be I is equal to 0 because it's index 0 at the left boundary. And we now have this point minus this point. And here I actually mean the point that is left to the left boundary. So this is outside our model domain. And therefore we also call this point a ghost point. However, if you evaluated this directly as code, it would take the last point instead, because remember when you index it like this, it takes the last point instead of the point before the model domain. Okay, so if this is a ghost point, we have a problem, right? Because it's not defined in our domain. But we can look at it like this. This whole expression has to equal 0, and the only way that that can equal 0 is that if uh, this ghost point is exactly equal to this one, because then the upper parts in the fraction here will equal to 0 and the whole thing will equal 0. So we can derive that the ghost point is equal to the point just right to the left boundary. And now we can use this information when we define the derivative at the left boundary. So we start by copying the diffusion equation here. We then replace the index, which is 0 at the left boundary. And we now substitute this one into the ghost point position, which would be here. And we can then get rid of this. So now it's all fixed for the left boundary. Now we have to do the same thing at the right boundary. And we can go down to, just copy this. And now I would be equal to n, because we are at the last point now. So our flux looks like this when it's discretized at the right boundary. Now it is the Cn plus 1 that is the ghost point, because that is one right of the right boundary. We don't know this, but again, we know that this one has to be equal to this one in order to get the whole term here to 0. So I will just write it's the ghost point, and therefore Cn plus 1 is equal to Cn minus 1. We can now define the derivative at the right boundary like this: n plus 1 and n minus 1. And now we substitute this one into the ghost point position. Good. So we have fixed the derivatives at the left and right end now, and we should be ready to run the code. Let's see what it says. Okay. So here we have a quick decline. Whoops, I think that's something. Let's run it again. Right, that looks right. So at index 0, the blue line, which is at the left side of the pipe, we have a quick decline in concentration. And we see that at the other positions, some of them increase a bit over the 1000 seconds. But if we simulated it for a longer time, we should reach equal concentration all over the pipe positions. Okay. But what then happens if we change the spatial step size? Let's put it to 0.1 instead. And I will close this figure and rerun everything. So this looks totally different. We have a much slower decline in concentration. So now I want you to think about before class, why do you think this is the case?